For cladding and buffer. Core is nothing but fiber optics. There are two materials used. Mm, a plastic material where the light travels as a signal, where cladding is an outer material covered and buffer is the outer coating. Then the total internal reflection is a critical angle where the light bends and travels long distance as an information. So I already covered what is core cladding and critical angle and why light travels like that, like an information. That's for the whole knowledge of optical fibers. Now we'll talk about critical acceptance angle. Okay. There is a critical angle which is a total internal reflection happening inside the fiber. The acceptance angle is different. Imagine light coming from outside into the fiber. The acceptance maximum angle is the maximum angle at which the light can enter the fiber and the still becomes guided by total internal reflection. So 0A is an acceptance angle, maximum entrance angle for guided light. If light enters with this angle, it can propagate to the fiber. If it enters at too large an angle, it won't satisfy the required condition for total TAR and will escape into the cladding. Satisfy the required condition for TAR and will escape into the cladding. What is numerical aperture? Numerical aperture tells how much light the fiber can accept color or collect. For a fiber in air, numerical aperture is equal to sine theta alpha. Most generally, Na equals to N naught sine theta alpha, where N naught is the relative index of the outside medium. For air, N naught equals to 1, approximately equals to 1. So Na equals to sine theta alpha. Can I accept or collect? I think science. Uh, the critical angle is an angle in which a light bends, but the acceptance angle is the angle in which the light was entered. Okay, that's the difference. In numerical aperture, in fiber in air, Na equals to sine theta alpha, Na equals to N naught sine theta alpha, Na equals to sine theta alpha. Okay, for me, this is for air. Na in terms of core and cladding. For a step to index fiber, Na equals to root over N1 square minus N2 square, where N1 equals to core refractive index, N2 equals to cladding refractive index, and N1 is greater than N2. Therefore, sin theta alpha is equals to root over N1 square minus N2 square for air. This is the numerical aperture equation. This is also numerical aperture. What it is in terms of core and cladding, this is in terms of medium. So this is in terms of medium and acceptance angle. This is in terms of refractive indexes of core and cladding. Uh, the step index is fiber when n1 is greater than n2, therefore sin theta alpha equals to n1 square minus n2 square. Introducing the difference between the core and cladding refractive indexes becomes larger n1 minus n2, then Na is become Na increases when n1 minus n2 increases. The distinction to remove critical angle, acceptance angle. The minimum angle condition needed to require the core cladding interface condition for total internal reflection is the critical angle. The angle required for the total introduction is the critical angle, minimum angle. The acceptance angle is maximum at which the light enters. That's the angle of the light thrown from the laser. The laser is used at the signal is comes to the source of a laser, and it be the transmitter signals, the beam blinks in a way that for 100 milliseconds light travels like an information to the optical fiber. The numerical aperture, measure of fiber's light gathering ability. Na equals to sine theta alpha in air. If not, if there is another refractive index of the medium, then it is n naught sine theta alpha. N equals to n1 square minus n2 square root over n equals to root over n1 square minus n2 square for refractive index of core and cladding. So there are what is the particular way in which light can propagate to the fiber? The mode is a particular way which light can propagate to fiber. Light can travel to fiber. A particular way. Think of the fiber as path for light. Depending on fiber structure, light can travel along one allowed propagation. Depends on the fiber structure, light can travel along one allowed propagation pattern or many different patterns. So mode equals to allowed propagation pattern of the light. So there's a pattern goes the light in a for the laser sends the light in a information like the for a beam it takes one the output receiver takes the beams in a binary order. So this is a propagation pattern. Think of a fiber as a path of light depending on the fiber structure. The fiber structure, light can travel along one allowed propagation pattern or many different patterns. Single mode fiber, only one mode propagates. The core is a very small, typically around 8 to 10 micrometers in diameter. Because only one mode travels, very little mode travels. Because only one mode travels, very little model dispersion, very high bandwidth, suitable for long distance communication, used extensively in telecom networks, multi-mode fiber. Many modes can propagate simultaneously. The core is larger, commonly 50 micrometers or 62.5 micrometers. Different modes can take different paths and therefore arrive at different times. That causes model dispersion and therefore limits the bandwidth distance product. Why does multimode have dispersion? Imagine two light pulses enter simultaneously. So first let's understand what is a single mode fiber. Because one mode travels, only one mode travels very little. Here multi-mode travels. What is the meaning of mode? A fiber path is a light path depending on the fiber structure. Light can travel along one allowed propagation pattern. Only one mode propagates. The core is very small, typically 8 to 10 micrometers in diameter because only one mode travels. What is the meaning of this? Very one mode travels. Let's see the pictures. In the multimode picture, a green or yellow lines represent different propagation modes, not necessarily two separate levels. Multimode fiber. Yes, the same optical signal can occur multiple allowed modes in larger core. No, that does not mean multimode means multiple. A single optical source can launch light into multiple modes. Green light and yellow lines are two modes of propagation of light. Why does single mode look like this is an important picture. The picture is simplified. Simple mode does not mean the light is physically traveling as a perfectly straight way with electromagnetic field structure. It means the fibers very small core and refractive index structure allow only one propagation mode. The different diagram represents that mode as a straight looking line, but this is a representation of one allowed mode. Why do multimode fibers show bends? Because the larger core allows the different propagation mode. Some modes can travel nearly along with fibers axis, while others at larger angle. The angled paths are illustrating different modes that propagate repeatedly under that core cladding boundary. Because these modes can have different propagational paths velocities, they can arrive at different times. This is called model expression. And your laser question. Suppose one laser sends an optical pulse into a multimode fiber. The same input light can couple into several modes, so you don't need laser 1 and laser 2, one optical source, multiple modes inside the multimode fiber. This is a hmm, so for a single mode fiber, it doesn't happen because the area is smaller. Let's go to the topic here. So that's the difference between multimode fiber and model dispersion. The core is larger, commonly 50 meters or 62 different modes can take different modes here, meaning the dispersion is taking different modes from the same input laser beams and therefore arriving at different times that causes modeled expressions. Because of this propagational difference, they exist in a for different times. That's why that's causes model expression and therefore limits the bandwidth distance product. Why does multimode have dispersion? Imagine two light pulses entering simultaneously. B travels a longer path, therefore, they don't arrive at the exactly same time. T, T is greater than T. This is if you send many bytes, transmitted 1010, receiver 1010. The pulses can spread and eventually all of this is called pulse broadening. If the spreading becomes too large, the the transmitter sends light as a binary, receiver takes it as a binary. The pulses in the due to the optical fiber, the pulses can broadening. This happens. Pulse broadening happens. If the spreading becomes too large, the receiver can have difficulty distinguishing from one and zero. Because if the spreading becomes too large, the receiver can't know what is binary here. Single mode versus multi-mode. Number of modes, single mode is one, multi-mode many. Pore diameter small, multi-mode larger. Model dispersion very low, very higher here. Bandwidth very high, here lower. Distance long, here shorter. Typical use long distance telecom. Shorter links are LAN. Plans matlab plans plans means we know right. We have a LAN for computers connected with the LAN. Then internet comes. That's the LAN. And light information may loss. The light powers may loss. Like we expect a loss in I think transmission lines too. In the topic also. But here this is optical fiber. When light travels to a fiber, the optical power gradually decreases. This reduction in optical power is called attenuation or fiber loss. Loss equals to reduction in optical power. The main loss you should know are absorption loss, scattering loss, bending loss. Uh, three types of losses. Absorption loss. Optical fiber absorbs the power. Scattering loss. If any scattering are out of the critical angle, then there is a loss. Then bending loss. I think let's study absorption loss. Some of optical energy absorbed from the material of fiber and converted mainly into heat. So, light energy is absorbed as energy or heat. There are two broad sources: material and statistic absorption. The fiber materials itself absorbs some wavelengths of light. Impurity. or extrinsic absorption. Tiny impurities in the fibers can absorb light. I think we'll stop here. We'll continue later. As I'm uploading this in YouTube, don't forget to like, share, subscribe. Optical simply means the rate at which the light carries transfers or energy. In fiber optics, we usually measure in watts, or more commonly for communication links, dBm. Electrical power equals to electrical energy per time. Optical power equals to line energy per time. So if a laser is continuous sending light, P equals to 1 megawatts. After traveling some distance, P equals to 1 megawatts. The decrease is what we may call as power loss attenuation. The optical energy, how much total energy that light carries measured in joules. The optical power, how quickly that energy is being carried measured in watts. P equals to E by T. Higher received optical power general means stronger light signal. Photodetector. It's in the photodetector. Okay. So the meaning of optical power. The light when light travels through a fiber, the optical power gradually decreases. Means the light energy per time gradually decreases. This reduction is optical power is called attenuation of fiber loss. Loss equals to reduction in optical fiber. The main losses you should know are absorption loss, scattering loss, bending loss. Absorption loss. Some of the optical energy, example, absorption light energy is absorbed by fiber material or impurities. So the absorption loss of material is of two types. Material is material absorption, impurity absorption, or because we can also call it as intrinsic absorption, extrinsic absorption. The fiber material itself absorbs some wavelengths of light. This is called material absorption. Tiny impurities in the fiber can absorb light, like the water ions. Impurities can cause absorption. The other impurity absorption or extrinsic absorption. What is scattering loss? The fiber is not perfectly uniform at a microscope in the guided mode. So the guided mode is the normal guided mode is multi-mode and single mode. But due to scattering of light, it is not in those modes. That's what it is saying. Small variations in the material cause some light to be scattered in different directions. So because of the material, some light may scatter in different directions. The fiber is not uniform at microscopic scale. And microscope is means like we use a micro very we don't see it, but there is a microscopic problems in the fiber which causes the scattering of light. That is called scattering loss or realized scattering. Bending loss. This one is easy to visualize. If you bend the fiber too much, like this is a normal fiber, when there is a strong bend at a particular part in the fiber, some light rays modes can no longer remain properly confined by the core or cladding structure and can escape. There are two commonly used discussed types: macro bending, a large visible bend in the fiber; micro bending, a very small microscopic bends or distortions in the fiber. These can also cause optical power to leak out. So remember the three: absorption loss, scattering loss, bending loss. What happens? Fiber absorbs optical energy, light is reflected. Of microscopic variations, expressive binding causes some guided light to escape. Fiber attenuation is of three types: absorption, scattering, bending, losses. So this is enough for my preparation. One important measurement: fiber attenuation is commonly expressed in decibels per kilometers, meaning how much optical power is lost per kilometer of fiber. For example, if attenuation is 0.2 decibels per kilometer, then a 10 kilometer fiber has approximately 2 decibels loss of attenuation, ignoring other effects. Power loss means also known as attenuation. So Advantages of optical fiber continuation. This is short but directly relevant to your syllabus, my exam syllabus. Advantages of optical fiber: very high bandwidth, low attenuation, small size. Very high bandwidth means it can go long distances. Low attenuation means low power loss. Small size and lightweight means fiber is much thinner and it is lighter than metallic cables. Immune to electrical magnetic interference means you know what is electromagnetic interference. If you study transmission lines, you will understand what is electromagnetic interference. Electrical isolation. This is no direct in transmission lines. The wire carries electromagnetic waves. A normal power line carries 50 wire, but a transmission line carries a very large amount of frequencies, so generates electromagnetic waves and information is going as an electromagnetic wave that if wires are very closer then there is an interference happens, so that interference disrupts that information, that is called electromagnetic interference. Very little effect in optical fibers because that doesn't use uh, as a information not going as an electricity, it is going as a light source, so no electromagnetic interference in the optical fibers. Electrical isolation. There is no direct electrical conducting path between two ends of fiber. That's true. High the output is taken by my detector, photo detector. High security. It is harder to detect a fiber signal without physically interacting with the fiber compared with many conventional electrical transmission lines. High security. It is harder to detect a fiber signal without physically interacting with the fiber compared with many conventional electrical transmission systems. So, yeah, information cannot be still like low crosstalk. Light traveling in one fiber does not readily interfere with signal in neighboring fibers. Long distance communication because of high bandwidth, low power loss. Internet backbone, telephone data centers. Undersea internet is working on optical fibers. Fiber optic section is coming. Thank you for watching.